So welcome everyone again, and we will see here a just briefly shared screen. Welcome to our first Canada Summer Mentor Sessions, sponsored by Studica, who will host our final 5 sessions in person in August at Studica in Mississauga. We're most appreciative of our partnership with Studica and really have been enjoying interacting with all of you, both during the season and in the off season here. So as we have already discussed, here's our session schedule. Our introductions are now drawing to a close, and we'll be beginning session 1, the first of 2 75-minute sessions, punctuated by a break at 7:30 of 15 minutes. And then we'll finish off with some reflections. So with that in mind, I'm going to hand it over to Kaleb, and perhaps we can ask Kaleb to begin with an introduction and then proceed into FRC coding from this perspective of Team 1114.
Hi there. My name's Kaleb. I'm a programming mentor for 1114. I've been on the team since 2013. Started programming in my second year in grade 10. And I've been the head programming mentor since 2017. I'm just going to start sharing my screen here. Is that coming through?
Yes.
Great. Yeah, so today I kind of have 2 sections, 2 different presentations. The first one is just going over the basics of using the WPI lib and Java for FRC. And the second is going into the more specifics of how we structure our code and how we would approach a build season and programming our robots. As I said, mentor for 1114. Our team has been around for a while. We're a first Hall of Fame team. And we've actually used the same programming structure since we switched to the C Rio, which was when like Java was first came to FRC. And basically ever since then, we've been using the same way of programming with some modifications year to year and slowly building up. But most of how we approach autonomous has been unchanged since then. So I have a couple of videos of just various autonomous modes that we've done over the years, but I think, most people are familiar with them. I'll just go over our 2022 one just quickly to kind of show of the goal of kind of where you want to go, like what your end goal should be when you start programming a robot. Can you guys see this YouTube screen here? Yep. Okay, great. Yeah, so our robot's down here. We're doing the 5-ball autonomous mode, and you can see we're navigating the field, picking up the balls. The robot knows when it picks up the balls and to move on to the next step. It knows how to aim to the goal. It knows how to drive to a certain position. And basically, how do we get to that where the robot's actually doing things on its own autonomously? It definitely isn't easy, but if you kind of know what you're doing and have a plan, it can be a lot easier than it looks from the outside. All right, so going over basically the basic way to program a robot, which is to kind of keep all the code in one file and to use the timed robot framework. And I find this is really easy for teams that are just starting out. You can kind of use the joysticks, tell your motors what to do. You can do basic autonomous modes. If you're using sensors or motors like the Neo or the Falcon that have built-in encoders and built-in PID controllers, that can make things a lot easier as well, because then you don't have to write your own. So you can actually make a pretty impressive robot just doing something like this. So that's the one we're going to go over first. And then we'll go into how we structure things. And yeah, just as our team's philosophy for programming, we start with the most basic ways to control the robot, and then we add complexity if needed. So something like, for example, an intake, which is just a motor that spins forward or backwards, you don't need to do any kind of advanced control. So you just keep it simple. And then if you need something like a shooter that might need to be a little bit more complicated, then you work on that. But you don't want to overcomplicate things. We also like to use a lot of the built-in WPI lib libraries, especially for 2022. We used their Swerve library because it was our first year doing Swerve. And we didn't have any experience with it. Like we never did one during the off season. We just started it during the season. So we used a lot of the WPI lib built-in code, which helped a lot. Just as a general goal, we like to make sure that the robot code never crashes and that the code isn't a reason that the robot basically is sitting dead on the field. We want to make sure that the code is, reliable and pretty much right away when kickoff happens, we start programming right away. We want to make sure we have all the, components already programmed, and that way, if it turns out, oh, we actually aren't going to do this, it's much easier to delete something later on than to, in a panic, oh no, our competition's in 3 days and we haven't programmed this, we got to add it. A main goal with the way we program the robot is to make sure that it's really easy to read the code and know what it's doing. That way, in between matches, especially, if you're in the playoffs and you have a quick turnaround time, you want to be able to make changes to the code easily and without things going wrong. So that's kind of our guidelines. Which motor controller, sorry. Oh, just the, if you use the Neo brushless motor, they come with the Spark Max, which can do PID control. Or if you use Talons can do PID control if you have an encoder connected to them. And also Falcon 500 motors have the speed controller and the encoders built in. Now, obviously, they're a bit more expensive than just, Sims and like a Victor, but there are a lot of benefits to using those. So just going over the basics of programming a robot. Basically, what you're doing is you're taking in inputs and then setting outputs. So the inputs would be the drivers touching the controls or sensors on the robot. So encoders, gyros, vision camera, limit switch, things like that. And then the outputs are basically, the most used ones are in motors and then pneumatic solenoids to move air cylinders. And then sometimes you can use a servo or like a relay, which is just like an on and off. All right. Yeah, so VS Code is what's used for Java and C++. If you go to the WPI lib website, there is like instructions on how to download and install that. We're not going to go over that in this one. And it has templates for the robot projects. And then this is also how you download the code to the robot. So we're going to be using the timed robot template, which has 3 basic modes, the disabled mode, the autonomous mode, and the teleoperated mode. And basically each mode has 2 functions, the initialization, which happens only one time, and then the periodic function, which gets called in a loop. That's why it's called timed robot. And basically it happens every 20 milliseconds. So anything you put in there is going to get called over and over again. And that way you don't actually need to put any kind of while loop in your code. It just does it on its own. And when we're writing this code, basically, we're going to be needing to create objects. Just hold on one moment. All right, I'm back. Yeah, so basically, since it's Java, what we're going to need to do is use the objects provided by WPI lib to sort of access parts of the robot and the controllers. So the three most basic ones that we'll need to create a joystick. So that way we know what the drivers are doing. We'll need to create a motor controller. So in this, like you can use a Victor, a Spark. They're all pretty much the same with the simple ones that just set a motor output. It doesn't really matter which one you use. And then also solenoids. So that's for pistons. So if we head over to VS Code, when you first open it up, you'll have this little icon over here, which is like the WPI logo. You can click that and then create a new robot project. From here, you want to create, you select a project type. We want a template. We want Java. And then we want a timed robot. I use Skeleton because it just has less like unnecessary stuff in there. Then basically we'll just make a new folder. Do a project name. We like to just do Simbot and then whatever year it is, but you can just do whatever. Enter in your team number, and then you click generate project. And then this would basically have created the basic template, and then it's going to go ahead and actually build the code the first time you create it. So basically most of these you don't need to worry about. The main thing you need to worry about is the SRC folder, Java, and then here's where the actual code will go. So there's the main, which you would never need to change unless you're doing something advanced. So you just leave that blank. And then here is the actual robot.java. This is where you'll write the code. So as I said in the slides, there's basically an init and then a periodic for every mode. So there's, autonomous, teleop, disabled. There's also test, but you don't need to worry about those. And then so here is where we'll basically be creating the joysticks and the motors and then setting their outputs. So when we're first getting a robot up and running, we like to focus on teleop first. That way, it's a lot easier to test things because you're actually holding the controllers and pressing the buttons. And basically, we're going to, first just have it where it's, you press a button and then the motor does something, and then you add the sensors in later on. So the first thing we're going to need to do is create the objects. This is for what we want to be using, so the joysticks and the motor controllers. And we're going to create them pretty much right at the robot.java. This one. So right here, you can just do like joystick. And then as you're typing, it'll start automatically suggesting to you based on what you're typing, things from WPI-lib. So we can just click that. It'll automatically import it. So we're making a joystick. We're going to call it driver controller. And now we've created it. But right now, this object, this joystick object is actually, it's null, like we haven't initialized it. So what we can do here is in robot init, go driver controller equals new joystick. And then inside here is basically which port it's in. So we're going to do port 0. Most things in FRC use 0 as the first, not 1. So that's just a thing to keep in mind. And if we had a second controller, what we could do is just basically copy this. And then instead of putting in port 0, we'd put in port 1. So now we've created the joystick controller. Now we're going to do one of the motor controllers. So it depends like what brand you're using, but the code is going to be the same. So we can do a Spark, or we could do, which I think is what comes in the kit of parts now. You can also do Victors or Talons. So we're going to do Spark. We're going to call it drive left 1. Usually most robots have 4 motors on them for the drive base. So we're going to just and then we have to do the same thing where we say and then also what you can do is if you're not sure what to put inside of the brackets here, if you hit control and then space, it'll pop up like a little helper for you. And basically it'll say what type of variable it's expecting. So an int, basically that's a whole number. And then it also kind of gives you a little message here. Usually most of the WPI-lib stuff will have like an actual description of what it is looking for. So that's really helpful. Yeah, so it's just saying the PWM channel that the Spark is attached to. So this would be on the RoboRio, which PWM port. Now, if you're doing something using CAN, it would be whatever CAN ID you set that to when you're actually connected to the robot in the configuration. So yeah, we can just start with port 0, work our way down. And then basically if you know, the electrical team comes to you and says, hey, we actually plugged this into port 5, we want to change that. Basically, you know, all you have to do is change the 1 to a 5. So now we've created the objects that we'll need. Now all we have to do is go into our teleop periodic code and start basically reading the value from the controller and then setting the motors. So what we're going to do, this is just assuming, you know, a basic, you know, tank, like a kitbot drive, 2 sets of wheels on each side, forward, backwards. And then if one side goes forward and one side goes backwards, that's how you turn. So to program that, what we'll do is every loop, we'll make a variable called X. And this is going to be the X axis of our controller. So now to get that, we're just going to say driver controller dot get axis, get raw axis. And then depending on the controller, this will be a different axis. When you have a controller plugged into the driver station, under the USB tab, you can actually see which number each axis is, and you can actually move them and see which ones are changing. So that's a good way to figure out which axis is which. So yeah, we're gonna make another variable called Y, and this is gonna be the Y. And it's probably not axis 1 and 0, but just for now. And I spelled something wrong. Driver. All right, so now basically every loop, this is going to make a variable called X and make X equal to whatever the joystick currently is at. So this is going to constantly be updating while we move the controller, which is good. Now all we have to do is set the motors to go how fast the joystick is. So for most motor controllers, you do dot and then set, and then inside here would be how fast you want them to go. What's really nice is that controllers go from -1 to 1. So, and as a decimal, so a -0.5 would be half speed backwards and all that. And what's nice is the motors go from -1 to 1. So what you can do is actually just tell the motor to be where the controller is, and that will just do a direct 1-to-1 mapping. You don't have to worry about converting anything. So yeah, we set the left to, And this is the long way of doing it. What we can do is actually make a function that actually sets all of the motors at once, and then we don't have to keep typing out each one over and over again. So that's something we'll do at the end. Now, for a tank drive, if we just set all of them to be the y-axis, basically we can only go forwards and backwards. What we need to do is be able to go left and right. So what we need to do is make 1/2 of the drive y plus x. So basically, if you're going forward and turning, it'll add them together. Now to turn, we need the other side to go backwards. So we need this side to be y minus x. And this is basically all you need to be like driving around with the drive base and using a controller. And if you don't invert the other side, then you won't be able to actually turn. Now, some robots have pneumatic cylinders to shift between high gear and low gear. Also, some robots have, let's say, an intake that can go up and down on a pneumatic cylinder. So we can just go over quickly how to use those. So instead of doing a spark, we're going to do a solenoid. We'll do intake because that's probably going to be more common. Most teams don't really use 2-speed gearboxes these days. So intake. Now, since the new control system just came out with the Rev components, this is actually asking which one we're using, either the Rev one or the old Crossroad Electronics one. So we're going to do pneumatics. What does that want? Module type? And then here we're going to do CTRE PCM and then channel. So this is what port on the PCM is this solenoid plugged into. So start with 0. And then it's a similar thing where basically you just do dot set and it will set the piston. Now, instead of being like a -1 to 1, like a motor, it's going to be either true or false because it's either extended or retracting. So what we can do is actually do intake dot set. And then this could be, instead of an axis, it could be a button. Now this would work as a toggle. So basically, if you're not pressing the button, it will be false, but then only when you're holding it down, it will be true. What you might want to do instead is have it a toggle. So basically there's 2 buttons, one to make it retract, one to make it extend. And for that, all you would need to do is have like a if. So when the button's pressed, you want to make it, let's say false. And then we're going to do an else if another button's pressed, make it true. And then we have to get rid of this because basically if you're setting something many times, whatever you do last will be what actually happens. So if we did this and kept this line here, this was actually what will be happening, not the if statement. So we'll just get rid of that. So now instead of it being while you're holding down the button, now it's one button will extend it, one button will retract it, which we generally prefer. That way, if you're in an intense match and you're, pressing a button really quick, you know that one button always is going to turn it off and one button's always going to turn on. Yeah, so we went over the arcade drive, which is basically having one stick handle forward, backwards, and turning. What you could do is make it so that you could have it like an actual tank where, let's say, the left stick on the controller just moves the left side forward, backwards, and then the right stick moves the right side forward and backwards. So for the driver to actually turn, you would have to put physically like one side up and one side down. But we find that when you're doing that, basically you don't have any hands free or your thumbs are too busy and you're not able to press any other buttons. So we like to keep it on one stick. And so basically we have a robot that can drive around. We could pretty much make, add the rest of our stuff here, like a shooter or an elevator or a climber, just by doing, if statements and buttons, and kind of fill this out. Now what we want to do is actually be able to do something in the autonomous mode. The simplest way to do autonomous modes is to use a timer. Basically, if for the first 1 second of auto, move backwards, and then after that, stand still. A lot of games have bonus points for moving across a certain line or into a certain zone. And basically, you want to start with the most simple auto and then work your way up. So the first auto is just moving out of that zone. And actually, at our first competition this year, we didn't even have that auto, funny enough. And then at the end of the year, we had that 5-ball autonomous. So it kind of shows the evolution of our programming during a season. Yeah, so that's a great question. In autonomous, would a timer or an encoder, or which the Neo is using, more accurate? So yeah, using encoders are definitely going to be more accurate and more consistent. This is just sort of the first step where you want to use time at the beginning. But then after that, you definitely want to try using encoders instead, because it'll be more consistent. Yeah, so just to do a basic timer, which you might want to do anyway, even if you are using encoders, because certain things like shooting a ball might not actually have an encoder. You might just, hey, run this thing for a second, and by the time 1 second has passed, we've probably shot the ball, which is actually what we did use this year. What we're going to need to do is have some kind of variable that's going to keep track of time. So what we'll do is, this is our real code. First, we'll just make a variable called auto start time, which is going to basically keep track of when exactly did the autonomous get enabled. So what we'll do is go auto start time equals system dot current time milliseconds. So basically, when auto starts, what we're going to do is write down and record what time it is right now. And then this only happens one time. So basically, we know, okay, auto started at this exact moment. Then what we can do is every loop check, okay, auto started at this moment. And then we know what time it is right now. So if we subtract the two, then we can figure out how long it's been since auto started. And then from there, we can do commands based off of, for 1 second, do this, for 3 seconds, do that, etc. So basically, right at the start of auto, we can make a new variable called current auto time. And that's basically just going to be equal to the current time subtracted by auto start time. Now, sometimes you'll see these yellow squiggly marks. That's just basically like a little warning message. That's not actually like an error. And then this is just saying that, hey, you made this variable called current auto time, but you're not using it yet. So like we can pretty much just ignore this because we haven't finished writing our code yet. But if you do see something like red, for example, that means there's like an actual problem. Yeah, so now we have, we're keeping track of how much time has passed since the start of auto. Now, just to make a basic auto that's going to drive straight, what we can do is say if the current auto time is less than 1,000. Now, the reason it's 1,000 and not 1 for 1 second is because it's actually right here. It's in it says millis, like it's in milliseconds, and there's 1,000 milliseconds in a second. So that's why we're going to wait for a whole second here. And then basically, we would just set all the drive motors. But instead of setting them to be X and Y, we could set them to be like 0.5. Basically, for 1 second, go at half speed. And then what you can do is do less than 2 seconds, you can do something. Maybe we want to turn. So we'll set the right side to be negative. And then now we're done. So we're going to turn everything off. So this would be the most basic way of having an autonomous mode that just drives over a line. You could also add other things like, okay, drive to a certain position, then fire the pneumatic cylinder, then turn on a, let's say an intake motor, stuff like that. And you can just build out a whole auto just using these time increments. Another thing you can do is instead of doing time, you could have a variable that keeps track of like what step you're on. And then basically, if you're on step 1, you could look at the encoders like from the Neo motor. And you could say in step 1, drive this certain distance, then move on to step 2. And then step 2 could be using a timer. So you can combine timers and encoders together. Another thing you can do is if you had, let's say, like a camera, you could have like another if statement that just checks like, is the camera aimed at a target within a certain amount of degrees? And then once that's true, then shoot the ball, as an example. And yeah, so that's pretty much everything for the basic single file robot. Does anyone have any questions about this one?
Just a quick question. I was noticing when you do X plus Y and X minus Y or vice versa,
Right.
plus or minus X, and there's a potential for the joystick controller to have a sum that's greater than 1. Does it cap it off at 1 or something?
Yeah, so when you do dot set, like you could do like 100 and it's still only going to go at 1. So yeah, it is going to cap it off.
I thought so. It's just that's interesting. I'd never thought of doing it exactly that way. I've always done the rotation plus absolute speed kind of approach.
Oh, okay. Yeah, and like that's pretty much going to give you the same result. This is just like the basic way of doing it. But yeah, like having checks like, okay, if X plus Y is greater than 1, make it just set it to be 1. That's not needed, but when you're doing other stuff, like if, for example, instead of doing it by like a motor output, if instead you're doing it by like a velocity, you might want to do like an actual like hard limit on it, and something like that where you're checking how big it is would definitely be a good idea.
Oh, that's great. Thank you.
Is there any way to test if the code are okay virtually without using
Yeah.
the actual robot?
Yeah, so what you can do is there is like some kind of simulator. We actually haven't used it, but what you can do just to check if the code will give you any errors or not is you can click the icon up here and you can build the robot code. So this is going to do the exact same thing that it does when you're downloading the code to the robot, except the downloading part. So it's basically just going to check, hey, can I compile this code? And it'll basically say build successful or build failed. So if we did something here like make an error by spelling something wrong, then we go to build the code, it's going to tell us that the build failed. And then if we scroll up, it'll actually tell us why. And it says here, basically, it doesn't know what drive FT2 is. It doesn't know what that variable is. So being able to read these error messages is pretty important. Obviously, when you're first starting out, it's going to be hard to know exactly what everything means. But if you're ever trying to get someone to help you, basically scrolling up and copying and pasting this message and showing them, that's going to help a lot, because then they're going to actually be able to figure out what's going on. And what's also nice is it actually tells you exactly which line and which file the error happens on. So it says right here, line 65. So when you have a more complicated robot, and if you have more like a complicated file structure with multiple files everywhere, it's gonna be hard to know, okay, that variable, like where is it? So this will tell you where it is.
Okay, great. Thank you. And other than that, once I compile the whole thing, assuming everything's right, can be compiled, is there any way we can, as you said, mentioned before, is there any simulator that I can check it does what I want it to do at all?
Yeah, there is. I'm not too familiar with it, but I know they have tutorials on how to use it, and it's part of WPI lib. So it would, yeah. So this is just the main WPI lib website here. If you just search like WPI lib docs, and then somewhere over here, I assume there will be, yeah, robot simulation, and then it kind of shows you how to enable it and how to simulate it.
Oh, very good. Thank you.
Yep. Does anyone have any other questions?
I see a question about comments there in the.
Oh, yes, yes. Yeah, so I'll just open up one of our 2022 code here. And we do comments. Some things we don't comment because it's relatively readable. So like this function right here. Oh, I guess I should go over functions. This function here is basically just setting an intake motor. And because we use like speed as the variable, it's pretty obvious that this is going to set the motor to go a certain speed. So you could add a comment that says like sets motor to speed. But we like to code in a way where just based on the name of the functions and the variables, it's pretty easy to understand what's going on. Obviously, there are certain things like probably somewhere in our swerve code, yeah, where like we want to add comments to kind of explain what each thing is doing. And then also when you're just testing stuff out, or if let's say you're at, this was like a lot of this code is from when we were at the World Championships, and we haven't actually cleaned it up since then. So some of this stuff is like, we realize, we actually want to switch from RPM control to just like output control. So we just like added comments to get rid of all the RPM stuff. Yeah. Yeah, that's a good question as well. How do we test the code without having any robot? Yeah, what we do is we either use like a previous year's drive base and just kind of have it driving around on the field. But obviously you're not going to be able to test out things like the intake or the shooter or anything like that. Honestly, we just wait until the robot's done and start working on it. But you can test it in the simulator as well. But what we usually do is we write all the structure, and then from there, once we have the robot, it's just a matter of like tuning it and making sure everything is plugged in and like going the right direction. Yeah. Oh yeah, I guess I'll just quickly go over. So as I was saying, in this code here, it gets a little bit annoying having to type out all these 4 lines just to set the drive base motors over and over again. So what we can do is just like how there's functions here, we can make our own function. We can call it like set drive. And then basically what you put inside this brackets here is what like the parameter the function is going to use. So we're going to use a double, which is basically just any decimal number. And we're going to call it, we can just do double for Y and a double for X. That way we can just kind of go like this. And then now instead of copying and writing out all these 4 lines, what we can do instead is just do this dot set drive and then YX. So basically this function is kind of like a shortcut where if you replace this function with what's happening inside here, it's going to do the same thing. It's basically just because we're lazy and we want our lives to be easier. And now here, instead of using the X and Y, we just type in like the value we want it to be. So when you're making like a really long autonomous mode, having functions that can kind of simplify stuff will help a lot in keeping the code more organized. Yeah. So now it's basically doing the same thing where it's driving, turning, and then driving again, but it's like a lot less lines of code. Okay, so we got 2 more questions. What is the best way to have your code print out values for debugging? System out print line doesn't seem to work in this environment. Yeah, we actually do use system out print. It does work, but only when you're actually like running on the robot. Another thing you can do, so let me see, where do we system out? I know some stuff we just have it as a like a debug thing. Another option instead of doing system.out, if you're trying to debug, is using what's called the smart dashboard. So for example, you can put numbers and get numbers from the smart dashboard. Just trying to find like a nice simple way that where we do this. I think in our IO, right? Yeah. Yeah, so basically it works just like system out. So for example, if I did like system.out.print line, add quotes of like, I don't know, drive encoder value. And then we do like this dot. I don't know. I'm just like making something up here. Yeah. So this would work. It would basically print this value. Need a plus in here to the driver station. It has like a little in the bottom right corner has a little box where it will print out anything that you're calling with system.out. But what you can do instead is use something called Smart Dashboard. And that's basically, it's like a separate program that runs while you're running the driver station. Do I have driver station on this computer? No. But basically it can display values as well. So we use Smart Dashboard a lot because not only can you put values like basically like system out, but you can also retrieve values back. So what you can do is when you're first tuning something, you can put it on the Smart Dashboard, and that way, instead of having to adjust your code and re-download code every time, you just change the number on the dashboard and it will change the code like on the fly. So that can save a lot of time when you're trying to tune stuff. And then there was another one. And then is swerve drive coding much harder than tank drive? It really depends. I would say if you're just trying to have a robot that can just drive around, tank drive is definitely going to be simpler. Because basically, you know, this is all the code that it takes to move. And a swerve drive definitely takes a lot more than that. because not only do you have to, go forward, backwards, and steer, but you basically have 4 individual corners of the robot, and they all need to point at a specific angle and then move. And then obviously you can move forward, backwards, sideways, and turn all at once. So there's definitely a lot more complexity, and you need a lot more sensors going on. But once you do have it working, using it, like making autos with it and stuff like that, we found it to be pretty similar to a tank drive. It's just getting it running is the hardest part. All right, any other questions? Okay, so from here, we can go over basically the next presentation. Our break is in 15 minutes, so we can kind of get started here and then finish it after the break. So this is basically, once you get to the point where, okay, we can make, a basic robot. Chat here. To use time robot. Yeah, so we're gonna get into that right now. How we program, and yeah, we do use timed robot. Actually, we don't use command based. The reason for that isn't because like command based sucks or anything. It was just because when we were first doing Java, command based didn't exist back in 2009 or 2010. And so basically our programming mentor at the time, who's the teacher at the Governor Simcoe High School, teaches Java there, he basically came up with like a command based before command based existed basically. And since then we've just been reusing the same code every year, but our code is publicly available. So if other teams want to use that, they can use that as well. A lot of the same concepts apply to command based, but we find that command based, it's like really hard for new students to get into because there's so much going on, and we kind of like our structure a little bit better because it does work in a timed robot way. So a lot of the things that you learn doing a basic timed robot in one file applies to doing our robots, where command based is kind of like a totally different thing. Yeah, so yeah, we already did that. Yeah, so how we approach programming, it's similar to command based, where you have different subsystems. So for our 2022 robot, for example, we have a drive subsystem, an intake subsystem, a shooter subsystem, and then a climbing subsystem. And then we'll kind of go into how we make our autonomous modes, how we use sensors, including like vision cameras, how we actually control each subsystem using state machines, and then basically just some general best practices that I've learned over my like 10 seasons programming. Yeah, so just like before, we want to start simple. We want to use WPI-lib. And yeah. So basically, once the game comes out, oh, we have a message here. It works fine. We were finding that one side is running slower than the other. Using controller, the code is simple. Much is what you use for troubleshooting. Yeah, so if you're having a problem where one side is going much slower than the other, is that like you're printing out the speed and you're noticing that the value you're printing out is slower? Or is it like in real life it's moving slower? Or is it both? Like it's a real life and the printing out is also saying that it's going slower? As reported by Neo. Okay. And like also in real life? Like as it's driving? Okay. Yeah, so if your code's really simple and one side's moving slower than the other, there's a few other things it could be. It's possible that the speed controller, the Spark Max, has some saved settings. So there's a function you can do to reset the Spark Max, and we actually do that for our motor controllers. Basically, the second the robot turns on, we actually just restart and reset all of its, we do a factory default configuration. There's a similar function like this for Neos. So that would be something I would try. because this way, if you have, let's say you something breaks and you're like, okay, we're going to replace this. Let me get a Neo from an old robot. That might have some other configuration saved on it. So you want to always in your code factory reset it. That way, if you're swapping something, in between playoff matches, you don't have to worry about reconfiguring it. Now you are going to have to reconfigure its CAN ID, but you won't have to reconfigure everything else. But if you do the factory reset and it's still going slower, I would check the wiring, make sure there's no loose wires, because if something's has like a very thin wire, it could be drawing a lot more current and going slower. Then other than that, I would just check mechanically. If there's two motors on each side, make sure both motors are actually moving, not just one pushing the other. That could be the reason why one side's going much slower, because it's actually only one motor fighting the other one or pulling the other one that's not moving. Other than that, it could be a mechanical thing where one side has a lot more friction than the other. That's the troubleshooting steps that we would do. Yeah, so basically how we approach the build season from a programming point of view is basically once we see the kickoff video, we take one day to have everyone kind of read the manual. And then from there, we start prototyping, coming up with ideas, brainstorming. For 2022, we didn't do any of that because we were all remote. But luckily for programming, a lot of our programming, we don't actually need to physically be there. So we just pretty much started programming the robot day one of the game coming out. And so what we do is we just take our last year's code, copy it, and then remove all the parts that were specific to that robot. So basically, we would go in and say, okay, this is our our 2022 code. We would just come in here and go, okay, all these motors, we can just delete these, and we would just basically just make everything blank. And then that way, we would just come in and then add in the stuff that we end up needing later on. And since our code is on GitHub, we can always reference it. So we don't have to worry about we're deleting something permanently, because our old code is posted on GitHub. And that's actually the reason why we can use it. To reuse code, you need it to be publicly posted. So yeah, we would just go through and start clearing out parts that aren't going to be relevant to this season. So we would get rid of most of the subsystems except for the drive. In 2022, we actually got rid of the drive too, because we went from a tank drive to a sword drive. So basically nothing was going to transfer over. And then basically right away, okay, our robot's going to have a way to drive, most likely. It's going to need to be able to pick up the balls. It's going to need to be able to shoot them. Maybe you have a climber, maybe you don't, but you can at least create the code for it and then kind of change it or delete it if you don't end up having one. Yeah, and then basically getting into our actual code here, what we do is what's called a Singleton Pattern. This is basically to prevent us from accidentally creating two of the same thing. So for example, if you create a motor, like an intake motor, and you say, okay, this motor is going to be in port 2. If you create another motor and say it's also in port 2, it won't give you any errors, and you'll be able to build your code and everything will be fine. But if you actually download this code to a robot and try and run it over and over again, the robot will keep crashing. And inside the error message, it will basically say, I can't allocate this motor to this port because this port's already being used. So what we do is we use what's called a Singleton pattern so that we don't actually accidentally create two of the same file. And basically that would lead to because we would make this intake, then if we tried to make another one of these files, we would make this intake again, which would then cause that error. And basically to do that, what we do is we make a variable a static variable called instance. And then all we do is when you create this an instance of this class, we use the get instance function. And basically all it does is it checks, is my instance null? Basically, is this the first time I'm being created? If it is, then it will create itself. Otherwise, it will just return the one that already exists. So this is kind of like a pretty advanced Java thing. So if you're not following along, I wouldn't worry about it too much. But it's just one thing that we do to make sure that we don't ever accidentally create two of the same file. Because when we're working with so many things, it could be hard to keep track of if you've made it before. So by having this, it kind of is like a protection. But certain things that you do want to have multiple copies of, let's say like a PID, that won't be singleton. That would just be a normal class. It's just things like the motors, any of the subsystems. You don't want to have two intakes running at the same time, like two copies of the same code running. Stuff like that will be using the singleton pattern with the get instance function. So basically, most of our robots start with the IO file. This is basically where we create all the motors, we create all the sensors. This is also where we set all the motors, and also where we can, if we're doing something like a Neo or a Falcon or a Talon, this is where we configure all the built-in parameters. So like current limits, PIDs that are built into them. Yeah, basically it's similar to how we had that that single file robot, where we basically come in here, we write, okay, we're gonna have this type of speed controller for this motor. We got the shooter, we got the drive. Actually, the drive isn't here because we do things differently for the swerve drive. But yeah, we have some solenoids for the pistons on the robot. We had an LED strip. And then basically what you do is inside the constructor, just like how we did on the this robot in robot init, we're just setting, hey, this motor's in this port, this motor's in that port, and so on. And then same with the solenoids. And then here's just us setting all the stuff you have to set for like the swerve drive, which is a lot more stuff because you have two motors plus an extra encoder. Yeah. And then this is just where we configure all of our speed controllers, certain current limits, setting them in brake mode or coast mode. Some of them you can tell motors to follow each other if they're in CAN. You can do current limits, stuff like that. So basically the IO class handles all of that. And then what we do too is we basically just every cycle in our update function, this is where we put basically just debugging information about our sensors. So we have like a light sensor, which basically is on or off. So we're just putting that Boolean on or off, putting numbers for different encoders, what our shooter RPM is, stuff like that. Yeah, so the difference between brake and coast mode, basically it's a setting you can do on the speed controllers physically. There's a button you can press, or you can do it in software if it's a CAN based speed controller. The difference between brake and coast mode is in coast mode, when you turn the motor, when you tell it to go to 0, basically the motor will just shut off and it will just let itself coast and roll. If you set a motor into brake mode, what it'll do is when you tell it to go 0, it'll basically turn the motor against itself and it will try and slow itself down. And that's without using any kind of PID or sensors or anything. Just the motor naturally will turn like inverted on itself and try and slow itself down. So if you have something like an elevator where you want it to like stop in a position, we always set those into brake mode. Something like a shooter, you probably want to keep it in coast mode. That way, if your shooter shuts off, it's not like trying to fight against itself and stop moving, because there's a lot of momentum in shooters usually. So yeah, stuff like climbing, like our climber was set into brake mode. Our drive base was in coast mode just so it was a bit smoother and when, suddenly stop when you stop pressing it, you kind of want it to just coast. Yeah, and then here's also where we do like for our swerve drive, we have to update our position on the field. So all that kind of stuff happens in IO. And now what we do is to set motors. We don't actually do any of our like joystick, like in the single file robot, we had, basically, hey, read the joystick and then set the motors. This one just takes the motors. It doesn't do anything with the joystick. So what we do is basically make these public functions called like set intake motor, set intake wrist, which is the pneumatic cylinder, set the climber cylinders, and basically other files are going to use these functions to set the motors. And then there's also, so there's sets, which basically takes in where you want it, like how fast you want it to go, and then tells it how fast to go. There's also gets, which basically tells you like, hey, this sensor is at this speed. Like for example, with our shooter, we're taking in from the Falcon, you can read how fast it's going. And then you just convert that from whatever units the encoder has into RPM. So we're dividing it by how many ticks are in one rotation, holding it by 60, and then by 10 to get it into minutes. Yeah, so yeah, we can definitely go over PID for sure. And then I see your 2020 code in GitHub, not 2022. Yeah, so basically during the season, we keep our code private, and then usually right around the Stemley Cup time after that event, because it's our last event, so all of our changes would have been made. That's when we post our code publicly. So that's when we're going to make our 2022 code public. But pretty much all of this structure stuff is very similar. But in 2020, we actually had a separate, instead of IO, we actually had one for output and one for input. But what we found is since so many of our motors had sensors built in, it didn't make sense to separate them. So we kind of combined everything into just one input and output file. And yeah, we do put our code on GitHub so anyone can get it. Here, I'll just go there right now. So yeah, just github.com/Simbotics. Has most of our old code. So this is private, so you guys won't be able to see it. But all these other public ones you guys can see. So we have from 2015 till now as public. Our older code, some other mentor probably has it on like a zip file or something, but we didn't really use GitHub back then. And actually a lot of these, you can see that there's just one commit. That's because we originally used Bitbucket instead of GitHub. And just this year, we transferred everything over to GitHub. So it's just like one copy that we did. There's no actual, but if you look at our 2022 code, because I know some of you were curious about like GitHub and how it works. Basically, you can, all the code basically is shared by everyone. And then what you do is as you make changes to the code, you do what's called a commit. And that's basically adding your changes to the main repository. And you can see here, actually, it'll tell you when this folder was last changed. So some of these were from 3 months ago, some of them were 2 months ago. So we've changed our autos more recently than we've changed other parts of our robot, which makes sense. And then if you go in here, you can see, okay, which thing did we actually change? So here's what we did at Worlds. We made a couple changes by adding, changing our auto a little bit. And it just tells you like what line was changed, what it used to be, what it currently is. And it actually tells you over here, like which files got changed. And so yellow means it got changed. And then green means we added a new one. So we actually created a new auto at worlds like on the practice field. Yeah, and then there is a way somewhere to see all of the commits that have ever been made. For newer teams or teams starting bigger change room, just using another team's 22 code. So personally, I would, if you can, look over the 20, like your old code. But if it, you just really don't understand it, I mean, personally, obviously I'm biased, but I would probably copy our code and then just kind of remove the things you don't need and kind of start from there. But you can also start from scratch, just do the single file robot and kind of go from there. There's also a lot of YouTube tutorials going over, like if you want to do command-based. So it really just depends on what you feel most comfortable doing. But I think our plan is going to be to try and create like a template, a blank template of our Simbotics code. And that way people can just copy it for next year and just use it as if it's like WPI lib command based. It's 7:20. Is our break now?
I think we had scheduled for 7:30. Doesn't really matter. If we're ready for a break now, we can come back. And
yeah, I'll just show one more thing real quick. Chat. I think your structure is easier to understand than command-based robot. I think so, but also, we're the ones who've been using it for so long, so it's hard to say from a neutral standpoint if it is actually easier to understand. I think a lot of like the actual things that are going on in the subsystems are a bit easier to understand. But that's just based on, the questions I see people posting like on Chief Delphi and stuff about command-based confusion some teams have. Yeah, I can't really say definitively. So yeah, so basically also at the start of the year, basically all the students make a GitHub account and we just create like a blank repository with just our, like see here, the initial commit. It's just the basic stuff. And then from there, we kind of fill it out. And then what we use, because Git can kind of be complicated if you're using it in like the terminal, and a lot of students might have trouble, doing Git commands like in a terminal. So what we like to do is get them all to get a program called Sourcetree. And it's basically a graphical way to use Git. So students don't need to learn how to use like a command line to handle Git. And so here's Sourcetree for our 2022 code. And what's cool about this is it'll show you when certain changes were made, who made them. So Nolan, he was our grade 12 programmer. He did most of the code for this year. And then every once in a while, like you'll see me do a little change, but a lot of these are when we're actually at our practice field, just working on one computer. So even though like I made this push or this commit, it was probably both of us working on this code. And yeah, and you can also see, okay, like there's these little green branches and different color branches sticking out. This is basically if two people work on something at the same time, you have to merge the changes back to the main branch. So there's not two different versions of the code. Usually we like to keep everything just on one, just to keep things simple. And then every once in a while, like someone will accidentally like not sync up to the latest version when they make their changes, but that's fine because you can just merge them together later. We can go over this more later on. But yeah, basically you make changes and then you click this commit button and it kind of tells you, okay, you've made these changes to these files. So I've added a blank space on this line. So what we could do is just click stage all, and then this will sort of set up these changes to be pushed to the main code. And we can type in here whatever our message is, and then we would click commit, and then we would click push, and that would push our code to the main branch. And then everyone else, they just have to click pull, and then their code will automatically become the same as mine. So yeah, you can see here, like, okay, we change some auto modes, which is usually what we mostly do at competitions, is just do slight adjustments to the autonomous modes. We don't usually end up having to change much else. Sometimes we'll do stuff like, okay, like here at the St. Mary's competition, we added a new state to our state machine. We also made our intake go slower when we're spitting out the ball. So little changes like that. And it's really good to commit as often as possible. That way, if something does go wrong, you can go, oh, okay, well, we have this code here that worked. Let's see what we changed. And then you can see, you know, you can just go back to the old code if something went wrong. Or you can see what changes were made that caused the error. Yes, that's a good question. What's the easiest way to program multiple autonomous modes and select one? Great question. So let's say, just an example in this single file robot here, what we can do is just make a variable called like auto mode. And then what we can do is right here, right before we actually like run our auto. Let's say this was our main auto, but now we want to make a second one. What we can do is say like if auto mode is equal to 0. So that's just one thing you kind of have to know about Java. When you're setting something to be something, you do 1 equal sign. When you're asking how much is this, then you do 2 equal signs. So you're saying like, is auto mode equal to 0? You do 2 equal signs. But if you say, hey, I want this variable to be 0, then you just do 1 equal sign. But that's stuff that students, I know some of you said during the intro, like some of your students are doing some intro to programming classes. Basically, we try to encourage like our programming students, like, hey, make sure you're like taking the programming courses at school. We used to have a rule where you actually can't join the programming team unless you've done programming courses, but that was back when the programming teacher was actually running the programming sub team. So he just kind of said like, hey, like, I'm not going to teach you everything in my class from the ground up. Like during robotics, you should just do my class first. That'll make your life a lot easier. So things like that, it's just Java stuff. You can have students take like an online Java course, like an intro to Java. That can help a lot. So yeah, basically we have a variable keeping track of what auto mode we want to do. And then what we can do is say, okay, if auto mode is 0, do this. And then else if auto mode is 1, then we can have a totally different auto. So let's say, you know, we back up for 3 seconds and at full speed. Now, to actually make this something you can select before the match and not have to download code every time, one way to do it is with the smart dashboard. So what you can do is wait when your robot is turned on in robot init. You can do smart dashboard dot put number. So auto mode. And basically what this will do is it'll just put a blank variable called auto mode on the dashboard. And then what you can do is when auto starts, you can just do auto mode is equal to smart dashboard dot get number. And then this is important here, this default value, basically if it can't find anything on the dashboard with the same name, what should it use instead? So we want it to be 0. Why is this wrong? Oh, okay, so get number is, which one is int? Oh, I made auto mode an int. Okay, yeah. So what we could do is we could either make auto mode a double, but that won't work, like, because sometimes doubles can be not exactly 0 or not exactly 1. So what we can do instead is go like this. And this is basically going to convert this double, which is again a number with decimals, into an integer, which is just a whole number, like 0, 1, 2, 3. Just by putting this in brackets here, it's going to convert this. So that's just a thing that students can learn, and people would learn in a Java course. And so basically, this would be a way to select an auto. Basically, right before the match starts, it'll say, hey, you can just type in what auto you want to do, number 1, 2, 3, 4. Another way you could do it is just have it so if you press a button on the controller, it selects your auto, and then the dashboard is only showing you which auto you selected. And that way, if the dashboard for some reason isn't loading, you can just press the button and it's going to be set. So yeah, you can do that. Obviously, that code can't go in teleop or in auto because it needs to happen before the match starts. So if you want something to happen before the match starts, you can put it in disabled periodic. So when your robot is just sitting there, you'll be able to change the auto. And that's actually what we do exactly in our code. In disabled periodic, we just check, hey, we update what auto mode we're doing. That's what this function does. So you can do the same thing. And yeah, we just check like, hey, are you pressing a button? And that's what auto you should be using. Like, you press one button to go up on the list and then one button to go down on the list. And then here is all of the auto modes that we have. So like a 2-ball auto, 5-ball auto, fender auto. And then we always have a default mode, which doesn't do anything, just in case something's broken on the robot. You don't want it to try and do some crazy, 5-ball auto when part of the robot's broken and do more damage to the robot. So we always keep this default mode that does nothing as an option. It's also good because if someone accidentally clicks on enable when the robot's sitting there in the pits, default mode is the one that's first selected, so actually nothing will happen. So it's just kind of a safety thing as well.
So thank you so much, Kaleb. We've come through the first half of our programming session so far. We'll take a little bit of a 15-minute break and return at about 7:46 for the second part. Thank you very much, Keen. And we'll see everyone momentarily. And welcome back to the second part of our evening's proceedings. Just having finished our break, we'll go on to our second section, and welcome back, Kaleb, with some really interesting commentary about 11.14's programming practices. Thank you very much again, and over to Kaleb.
All right. You guys can hear me, right? Okay. So yeah. Basically, we were just going over how similar to the single file robot, where you have to create the motors and the solenoids, we do the same thing, just in a separate file, the IO file. And yeah, this basically just handles setting all the motors and also reading all the values from the sensors. And then it's up to the other subsystems to actually take in that information and use it. Yeah, so the next file we're going to go over is our driver input. So similar to the single file robot, we need a way to read the controller. So we have a separate thing just for the controllers. And what we do is we actually have a different class for each type of controller we could possibly use. Now, we always just use the same Logitech basic controller But if we were to use, let's say, an Xbox controller or a PlayStation controller, we would make our own class specific to that. And then from there, we would create one of those inside driver input. And as just a general best practice, and the reason why we use driver input the way we do is instead of having in your teleop code saying, joystick dot get raw button 4, we want to be more specific so it's more understandable when you're, in the heat of the moment trying to change something. So what we would do is you could label it like get the red, get green, get yellow, get blue button, or get left trigger, get right bumper, stuff like that. But what we even do beyond that is we actually label it based on what we want it to do. So like we could have an intake button, a shoot button, an aim button, a drive turn button, or the stick, stuff like that. So if we go over to our F310 class, this is basically we create a joystick, just how we did in the single file. And then here what we do is instead of saying like raw axis 0, we label it as like the left X. And raw axis 2 is the left trigger. So this is basically just mapping these raw values to the actual buttons as they're labeled. So like the green button is button 1, blue button is button 3, so on. And then also for the D-pad, it works differently. It kind of goes in like degrees from 0 to 270. But instead of dealing with that, we just kind of treat it as if it was just a normal button. And we just like kind of say, okay, if it's at this position, that's the down, and this is right, this is up, and this is left. Because when you're actually writing the code, you don't want to have to do something like this. You just want it to act like a basic button. You can also make certain controllers vibrate. This controller doesn't have vibration, so we can't actually test if this would work, but presumably on like an Xbox controller or a PlayStation controller, you could make the controller vibrate, which definitely could be used as some sort of feedback for the drivers. So yeah, we basically just have this joystick, which just kind of maps everything to what the buttons actually are. Then what we do is inside driver input, instead of creating 2 joysticks, we create 2 of those specific controllers. So we have one for the driver and one for the operator. And then we have, the drivers in port 0, the operators in port 1. And then here's where we go from being labeled from based on like the controller buttons to actually being labeled based on what the robot actually is using the button for. So for example, we have like the driver right X stick, driver left X, and then you can see here where we go this dot driver, that's just specifying, hey, we're talking about the driver's controller, not the operator's controller. And then we also do like right here is just it's just a dead zone. So basically, if the stick is less than 0.05, so 5%, just make it 0. Otherwise, then get the value from the stick. So basically, there's a small radius where the values will just be 0. And that's just to prevent the robot from moving really, really slowly, because a lot of joysticks, even when you're not pressing them, they might have a small value being returned. Especially if you have older controllers, they might have a little bit more of a drift going on. So having a dead zone is always good. Yeah, and then here we have like, okay, get our hanger out and in buttons. So we label things like exactly what we want the robot to do when the button's pressed. And then we use the actual like, okay, this is the red button. Intake on, intake reverse, intake up. And then we have stuff for the shooter. So shooting from different positions, all have different buttons, which we actually didn't use because we just use the aiming button and the shooting button. What we do sometimes is like for this year, we had shooting on the left and right trigger. Like one was for aiming, one was like shooting, like most video games. And we wanted to act like a button. So what we did is we just check if it's more than 0.1, then it will return true. If it's less than 0.1, then it will return false. So you're basically turning something that's from 0 to 1 into like true or false. Because the triggers, you can press them down halfway, like they can be, all the way, 0.25, 0.9, like anything like that. But we don't really care. We just want to know if we're pressing it or not. So that's why we can convert it here. And the reason we do this is, let's say in the middle of the competition, we want to change, okay, the intake on button, instead of being the green button, we want it to be the red button. You would just come in here and just change it from the right bumper to get green button. And then that would just change your controls just like that. And you don't have to go into everywhere in the code where you look at this button and change it there, because it's just called the intake button. It doesn't care what button it actually is. And inside here is where you can change what button it actually is. So if, let's say, halfway through the season, you realize, actually, our controls aren't that complicated. We don't need 2 drivers. We could just have 1 driver. You can come in here and then change all these things that are on the operator to on the driver. Just kind of gives you the flexibility. Yeah, and then we just have buttons. This is so when you press a button, it won't keep counting up over and over again. You have to actually let go of the button and then press it again for it to go up. So when we're selecting our autos, we have one button that kind of increases which auto is selected by 1 and one that makes it go down by 1. But if you're holding down the button, you don't want it to just jump all the way to the highest auto. So this is just making sure that you have to actually release the button and then press it again. Yeah. So yeah, that's driver input. It's relatively simple. Just kind of mapping the joysticks to specific functions on the robot. And then now we get into kind of the meat of where all the code goes, which is in the actual subsystems. So the reason we use subsystems is because we can write code for, let's say, a shooter, and that code can be used by both our teleop and our autonomous. That way we don't have to reuse code. And that way, let's say we wanted to change how fast our shooter was, we don't have to change it in 2 different places. We just change it in one place and it'll affect both auto and teleop. And the way we have our subsystem set up is that each subsystem has to have a function for first cycle, which is basically like the initialization. It has to have a calculate function, which is basically what just happens every loop. And then it has to have a disable function. So basically shutting the motors off. And then what we do inside each subsystem is we use what's called an enum. And that's basically a variable that can kind of keep track of what we want, but using like English names instead of using numbers. So instead of having, let's say, our shooter has 4 different positions, 0, 1, 2, 3, 4. Instead of that, what we could do is actually label them as, okay, this one's for the fender, this one's for the low goal, this one's for the high goal, etc. So you can kind of use words to make variables instead of numbers. So that way, when you're kind of, working on the code in between matches, you can just read it. Okay, if the shooter's in this state, fender, do this, instead of state 0. And you're thinking to yourself, okay, what's 0 again? I don't remember. So that's why we use enums. And then basically in each subsystem, you just have things for setting the state and getting what state you're currently in. And then every loop in calculate, it's basically just saying, okay, I'm in this state, do this. And so if we kind of look through an example here, let's go through, probably intake would be the simplest. So you can see here, we have a variable called intake state, which is just keeping track of what state our intake is currently in. So by default, we just have it in off and then up. We just have a couple of variables here just to keep track of how many cycles we're waiting for certain things. These, we don't actually use most of this stuff anymore. And then, yeah, we do the same thing that we did with IO, where basically we're just checking if we've already created an intake. And if we have, just use that version. That way we don't have 2 copies of this intake code running. And then here's that enum I was talking about. So basically, these are all the possible things the intake can be doing. And so like at the beginning of the year, you just kind of come in here and just start adding things that you think you'll need. And then later on, you might have to add a couple more and you can just add them on. It's just a big list. So we made a state called off up, off down, intaking down, intaking up, outtaking down, shooting, etc. And some of these other ones we added later on just as like a special case. Like for example, at the World Championships, we needed an auto that would spit out the balls really slowly, but it was just for auto. We didn't want to change how we spit out the balls in teleop. So we just came in here and made a special state called auto outtaking. It's just kind of like a quick thing you could do when you're doing things based on states. You can just create a new state and do whatever you want there, and it won't affect all the other states. And then basically what we do is we just have a thing called set state, which just says, hey, I want the intake to be doing one of these many things. So you can say, okay, set the intake to be off, set the intake to be outtaking. And then all you have here is get state, which basically just says, okay, what am I doing right now? So you might have some code that says like, okay, if the intake is already down, that means when I go to outtake, I want to be in outtaking down, not outtaking up, stuff like that. And then basically all we do is in our first cycle, we just configure our PID, which we can get into later, what this is exactly doing. And then all we do is every loop in a calculate, we just check. We're using a switch statement. This is equivalent to just having if, else if over and over. It's just a little bit cleaner of a way to write it. Basically, we just check, okay, what is our current intake state? And then we just say, okay, if we're in intaking down, do this. If we're in intaking up, do this. If we're off, do this, et cetera, for every state. And that way, you know, okay, if I'm in, you know, auto outtaking, you can just check, okay, it's setting the intake motor to be 0.3. It's setting the wrist to be true, which means the intake's extended. It's turning the indexer on. It's turning the top indexer on. And then it's also just kind of resetting a couple of variables we have here that we don't. And we ended up switching. We originally only had one light sensor that would keep track of how many balls we had. And then we had these kind of flags that would just check and keep track of if we've gotten 2 balls. But we found it was pretty unreliable. So for our second competition, we switched to just having 2 light sensors, one for the first ball, one for the second ball. That way we could just check the light sensors. We didn't have to worry about any kind of complicated code. So sometimes adding new sensors or doing mechanical changes might be the simplest thing you can do versus adding more complicated code. And then right here, we just as like a printout statement, we just print out, okay, this is what the intake's current state is. That way, when you're testing the robot, you can say, oh, you know, why is the motor spinning the wrong way? You can check, okay, are we actually in the right state that we think we're in? And if not, then you can kind of go through the code and figure out why you're not in the right state. So just doing things based off states just really simplifies things for debugging and also when you're actually writing the code itself. And then basically when you're disabled, just shut the motor off. So that's just one of our examples of one of our subsystems. And how we make sure that we can actually, that all subsystems will be following the same structure is we do this thing here where we extend subsystem base. You'll see this a lot in the command-based code as well, where basically this is like a template and so this is basically just saying any subsystem needs to have these 3 functions. Now they're blank, so the subsystem itself needs to fill in what you're going to do in those functions, but all subsystems need to have these 3 things. And that just kind of makes sure that, okay, the intake is going to have those 3 functions. Calculate, first cycle and disable, the hanger, the drive, the shooter, all those, they're all going to have the same functions. And now, so we have a bunch of subsystems. We have the controllers, we have the motor setup. Now we need to kind of actually have our code that's going to check, okay, you're pressing this button, tell this subsystem to do this and stuff like that. So basically we have just one thing called teleop controller and it handles all of the teleop logic. It checks what state you're in for each subsystem. It sets states for subsystems. The reason why we do it like this is by having all of this logic in one file, you can coordinate multiple subsystems. So you can make it so that when I press one button, the shooter and the intake do something, not just one at a time. So it just kind of helps with the looking at like the flow of the robot and how all the subsystems are going to interact with each other, which some years can be pretty complicated depending on your robot. Like our 2018 robot, originally the elevator and the intake had to be coordinated, and only the intake could only be in certain positions if the elevator was in certain positions. So having this kind of one class that kind of handles all of the teleop subsystems all in one place, you can avoid having them, being in the wrong spot. 254 does a similar thing like this as well. So yeah, if we go to teleop controller, basically what we do here is we create the driver input, we create the IO, we could create an intake, a shooter, a drive, a hanger, and our LED strip. We just have a couple of random things. And then basically we just, okay, we create an instance of each of those subsystems. We run the first cycle of every subsystem. And then this is our main teleop code happens in this calculate function. So first thing we check, okay, is the driver pressing the intake on button? Okay, set the intake to be intaking down. Otherwise, if they're pressing the reverse button, check if the intake's up or down and make the intake go up or down. This is our shoot button. And basically we just make sure that our hood is opened or closed, because our robot, the way our hood works is like there's like a locking mechanism. And if we're in the middle of being opened and closed, we don't want to shoot the ball. We want to make sure we're actually closed or open. So that's what this code is doing here. But yeah, just sort of like those advanced kind of logical things, you do them all in teleop controller. And then this is if we're not pressing either intake button, then we just shut the intake off. And then same thing here, if we press the shoot button, we want to check, okay, is the hood open? If it's closed, we also check, is the shooter at the right speed that it's supposed to be? We also check if the drive is aimed, which is like if the vision target is within like plus or minus 1 or 2 degrees. We also check if the drive is not moving. And then from there we can shoot. And then we also have, if we're not using the limelight, which is our camera, we still want to be able to shoot in an emergency situation if the camera is disconnected for some reason. So that's what this code does here. Basically, if you look at this else, it's like there's going to be if our state is in limelight shooting. So if we're not doing limelight shooting, then we use this code. And then if the shooter isn't at the right RPM, then we just keep it off. So it's just kind of a big if statement chain that just is checking, is it the right time to shoot or not? And by having all these states, you can kind of check each individual thing and set the intake accordingly. The shooter is a lot easier. You just check like, hey, which button are you pressing, and tell the shooter to be in that state. So there's the limelight shooting state, there's the fender shot, there's the launch pad, and then there's low goal, and then there's off. So if you press the off button, the shooter should be off. And then the drive, also pretty simple. Just like in our single file code, we have X, Y. Now for a swerve drive, you can also move sideways. So that's why we have 3 here. So we use like the left stick for translation and then the right stick for rotation. And then what we do here is it's called a rate limiter, slew rate limiter. This is a WPI-lib class that they made. Basically, it just limits how much acceleration you can have. So you just configure it at the start up here, how much acceleration you want. So like if a higher number means more acceleration and a lower number means less acceleration. And it will figure out, okay, you used to be going, let's say 0.2, your acceleration is, 0.1 every loop. So next loop, now we're going to be going 0.3. that was needed for our drive base because we found out if the driver, let's say, went full speed forward and then full speed backwards, the robot would just completely tip over. So we needed some way to limit our acceleration. So this is how we did using the built-in WPI lib limiter. And then basically, if the driver's hitting the aim button, the drive switches to the aiming mode. Otherwise, it just goes in the normal output mode. This is where we check, okay, if we're intaking, make the drive go slower. That way, the driver can be a little bit more precise. This used to be, I think like 0.6 actually, because at our first competition, we basically had no driver practice. So we wanted the robot to be a lot more controllable. So we just added this in. I think like a couple of days before the first competition, just to kind of help out the driver a little bit. And then what we do is, after, if we do this multiplication or not, we just set the drive to be going these speeds. And then the climber, similar thing where you just check, okay, are you pressing the button to climb? And then, so our climber could go from middle to high to traversal. So basically we would check, okay, are we, we're finished going to mid? Are we finished going to traversal? Are we finished going to high? And based on what state we used to be in, that's going to dictate what state we need to go into next. So, if you're on mid, the next thing you're going to be is high. If you're done high, then the next thing is traversal. So that's just kind of what this is doing. And then the out button, same thing, where if you're already on the high bar, now you're going to be extending, and these ones are retracting. Yeah. We also just have some thing to reset the encoders, just in case, I don't know, we fall off the bar or something and we need to reset our climb. We also have a manual mode where the driver can just manually move the arm up and down. It's usually good to have some type of manual control, especially for something important like the climber. And yeah. And then this is just like, hey, if we're in manual, this is like how we did the piston in the single file robot, where basically if a certain button's pressed, you set the piston to be true. Otherwise, you set it to be false. We also had a button to reset the gyro on the swerve drive, just in case it got messed up. Yeah. And then just right at the end, we have this LED code. We use the Blinken strip from Rev. And basically it comes with a little controller that you plug into the RoboRio, and it acts just like a motor controller. And then it also comes with a built-in LED strip, which can change colors. And then basically, depending on how fast you tell it to go, like as if it's a motor, like you just program it as if it was a motor, these different speeds correspond to different colors. And then what we did is we just labeled, okay, when the climber is extending, make it go red. When it's in manual, make it go pink. When it's, when the intake is on, make it green. When the camera can see the goal, make it yellow. When it's actually locked onto the goal, make it green. Things like that. It's helpful for both the driver to kind of know what's going on with the robot without having to look down at, let's say, system out printing something. Having the LEDs on the robot can kind of signal to the driver what's going on. And also helps the programmers too, because we're up in the stands, we don't really know what's going on. But if I can see, okay, this LED's red, when we're trying to aim at the goal, I know, okay, something's wrong with our vision tracking. And so it kind of helps you debug what's going on. Yeah, if we look at an example here, we started using this in 2019. We didn't actually get a chance to add it to our robot in 2020 because we were so rushed to finish the robot. But we did have it this year as well. It's a good one. I think this has a pretty good camera feed. Yeah. So yeah, you can see our robot. So in auto, we actually didn't set the colors, but so as we're driving around, blue means we have one ball. And then when we have two balls, we make it blink blue. So this is kind of where having everything in teleop controller, you can kind of integrate things. So the sensors and the LED strip kind of work together. And And then that way, when we're on the far side of the field, the driver can just know when the robot thinks it has 2 balls. And that's when it's time to shoot. You can see us down here actually. And then we also see, you can see the LEDs going like red. That means we're not aiming at the goal yet. They go yellow, and then now they're green. And then, yeah. So just stuff like that. Once you get into more advanced programming, you can kind of start integrating different subsystems together. So the camera, the indexer, the drive, the shooter, they're all kind of working together. And the driver doesn't have to really press that many buttons. He's just pressing the aim button and then the shoot button. And the robot kind of takes care of the rest. Yeah, and then we kind of did the same thing for climbing, where we start off red, and then as we extend the arm, it'll go green. As we're retracting, it'll go red again. Once it's good, it'll go green. So that way, if for some reason the robot doesn't lift up all the way, we can check, okay, did the code actually think that it was done lifting up all the way? Or was it like one of the encoders went wrong or something like that? So we can kind of see and debug in real time. Yeah, I forgot in that match, we actually climbed with like 0 seconds left. But yeah, all of that code that's handling teleop, the climbing sequence, all of that, it's basically a combination of what's happening inside of the subsystem and what's happening inside of teleop controller. Yeah, so we would definitely like to use whiteboards and kind of do like just in general, like, okay, if I hit this button, what should I do? And we kind of do a little flow chart of, okay, if I have 0 balls in the robot, I should do this. If I have 1 already, I should do this. If I have two of them, I should do this. We just like to talk things through, and yeah, we use whiteboards to kind of draw stuff out. And then from there, we kind of, the first thing we do with any subsystem is just, open it up and go, okay, what are the possible things this subsystem can do? And then we just start adding them in here. And then we start adding them in here. Okay, when you're intaking, obviously the motor needs to be turned on. And then the pneumatics need to be this way. And then we can, this is also where we're telling, hey, our LED should be this, the 1 ball, which is blue. Yeah, and then like, yeah, for like the shooter, for example, we only had a couple of states. We had off, fender, launchpad, limelight, local. And like half of these we didn't use. We pretty much just used this, fender and off. And then we also, the hood had 4 possible positions. It would either be opening, open, closed, or closing. It was like a pneumatic sequence that had to happen. And to handle that, basically what we did is, if you're closed, you just set the pistons to be where they are. But if you're closing, we needed a way to keep track of, how long we've been closing and all that. So we just used, instead of a timer, we just used like an integer that would basically increase by 1 every loop. So it's essentially a timer. So after 50 loops, then we would switch to being locked, for example. So this kind of stuff, definitely we, made a flow chart and we're trying to figure out what we should do. From there, we do these states. And then kind of teleop controller is where like you kind of have to do like a lot of extra thinking, because depending on how integrated the different subsystems are, you might need to do like a lot of checking. Like, okay, if I press this button, like, okay, is the elevator in the right state? Is the intake in the right state? Stuff like that. But for something like a shooter or an intake, it's basically each button just tells it what state to be in, and then that's it. Same with the drive. Pretty simple from teleop controller's point of view. All right, and so kind of gone over teleop controller. So now our autonomous structure. Basically what we do is we have an empty slot that we make, and we have one for each subsystem. So we would have one for the drive, one for the shooter, one for the intake. All of those slots can be running at the same time. That way you could be driving while the shooter's running while you're intaking a ball, for example. Then what we do is each auto is basically a list of commands. And then what we do is if there's 2 commands in a row that are for the same thing, like a drive 5 feet forward and then drive 10 feet forward, they both can't happen at the same time. So what happens is the auto will start doing the first one, and then we'll wait for the first drive command to be done before it moves on to the next one. And so we kind of can use that to have our autos do things in the right order that we want them to. So for example, if I go over to our auto modes and I go to our 5-ball auto, we can kind of see how the auto works first, and then we can kind of go into how we make these individual commands. Basically for our 5-ball auto, first what we do is we tell our drive what position it's starting in. So we just did 0, 0 for everything. We didn't really care where we were on the field. But if you wanted to track exactly where you were on the field, you could do that. But what is important is this angle. This is our starting angle that the robot starts at. Because our swerve drive was field relative, meaning that like if you push forward on the stick, it's always going to go forward no matter which way the robot's facing. You need to know what angle you start at to account for that. So basically every auto, if it started at a different start angle, we had to have that up here. And then right away in our 5-ball auto, we go to pick up a second ball. So the first thing we do is just set our intake state to be intaking. The next thing we do is turn our shooter on. So we set our shooter RPM. Our robot had a top. So if we hover over here, you can see there's top RPM, bottom RPM, EPS, which is like the epsilon, and then timeout, which is basically no matter what, after 2 seconds, this command will stop running. And then the epsilon is basically like what range of RPM do we need to be in to be considered like done. So we tell the shooter to go to 2,100 RPM. Once we hit 2,000, that's close enough, and it's going to say it's done and move on. And then what we do here is we drive to a certain point. So how we handled the swerve drive was basically wherever we wanted to go on the field, it would be an X and Y point with an angle. So basically, this is just saying drive 0 meters in X and 1 meter in Y, and also face -73 degrees. And then we have other stuff like a minimum velocity. So if you want to drive through a point, you can set your minimum velocity to be something that isn't 0. That way you won't slow down and stop. You'll just go through where you're trying to go. And then we have here a drive turn to limelight. So what this does is it'll just aim with the camera. But if the camera doesn't see anything, it'll go to this angle instead as like a failsafe. And then this sets the shooter RPM to be based on what the camera is telling it. So what we did is so we could shoot from any position on the field without having the driver to press like, 10 different buttons for each distance. We just use the camera to automatically calculate how fast the shooter should be going. So that's what this is doing. It's just calculating how fast the shooter should be based on the limelight, which is our camera. And then these commands here, drive weight and shooter weight. This is basically telling the auto, don't move on to these next commands until this drive command is done. So basically, it won't move on until we know that we're aimed at the goal. And then it won't move on until we know that the shooter is at the right RPM. So basically, our whole auto is going to stop until both of those things are true, or until this amount of time has passed and the commands just automatically say they're done, just in case something went wrong. And then what we do here is we just make it so the intake, instead of being intaking, we're going to override that. And now we're going to tell it to be shooting. So basically, once we've driven to the right position and the shooter is ready, now we're going to shoot the balls. And then we're just going to shoot for 1 second. And then we're going to go back to intaking because now we got to go pick up more balls. We're going to drive to 2 new points. We're going to turn to face a certain angle. I'm going to set the shooter RPM again because we're at a different position. we do the same thing. We make sure we're in the right position. We make sure we're at the right RPM, and then we shoot the ball again. And basically just kind of do the same thing over and over. Intake balls, drive to a certain position. And here this function, it actually only returns true when we have 2 balls. This is when we're getting the balls from the human loading station. So this way, even if the human player is slow or fast, because they're not always going to be doing things at the same speed, the robot will go as soon as it can. So basically, as soon as it knows it has 2 balls, it's going to move on, or after 5 seconds as like a failsafe. Because sometimes we wouldn't pick up the first ball, the human player would throw in the second ball, and then the robot's sitting there with only 1 ball. We don't want it to sit there forever. We'd rather it just go and shoot that 1 ball. Now that we've gotten these last 2 balls, we drive to a new position and just do the same thing where you just shoot, and then we're done. And that's the auto. So it is kind of, a lot going on with all these variables being typed in. But just hovering over, you can kind of see what each one means. So it's an X and Y position, is a theta, it's a minimum speed, it's a maximum speed, it's the epsilon, and then it's like just a number where, hey, if we've driven for 5 seconds and we still haven't gotten there, then just give up and move on. So this is what a basic auto, or not a basic auto, but this is what our autos would look like. And I find it's best to have the younger students kind of, they'll be the ones that kind of come in here and go, okay, the auto missed, didn't pick up the ball. Let me go in and change where we drive to. And then they'll just get more hands-on experience adjusting it. And then from there, they kind of get curious, okay, I've been adjusting this auto, but like, how does it actually work? And then they'll be more interested in looking into these actual functions and seeing how they work and learning more and more. Like when I started in grade 10, this was my job, just like adjusting things. Okay, the shooter was like a little bit too short. Let me increase the speed, stuff like that. And then you kind of you learn more as you go. Yeah. Yeah, so basically that's like a whole auto, but how do we actually make these commands that tell it to do certain things? So let's say we do this intake command. What you can do is click on a function and right click and click go to definition. It will actually open up that exact function for you, even if it's in a different file. So that's really useful when you're trying to figure stuff out. And here's the command itself. So basically we have this timeout, which is just how many seconds can this run for without being done. And then all we do is we just say, run the intake. If the indexer says we have 2 balls, return true, which will end the command. If it doesn't, return false. So basically this will just keep running until the sensor says we have 2 balls. And then all we do is in first cycle, turn the intake on. So it's going to turn the intake on, and then every loop, it's going to keep running the intake. And if it ever sees 2 balls, then it's going to return true, which means this command is done. And all of our commands basically work in a similar way. So if we go to, let's say, shooter, we have like set RPM. All this is going to do is it's going to take in a top RPM and a bottom RPM that we want to go. And it's going to just say, it's going to tell the motor, go to this RPM using this.io. And then basically what we do is we just check if the difference between where we want to go and where we are is within our epsilon, then we're done. So basically, are we within this range? And we make sure we use an and here. So basically the top and the bottom need to be going the right speed. Then we return true, which means the command's done, and it'll move on. So when we're using something like that, like setting the RPM, we set the RPM, and then once it returns true and says it's done, that's when we shoot the ball. That way we won't shoot the ball while the shooter is still spinning up to the right speed. And then each command basically has a certain subsystem it's for. So you can see here we have shooter, we have drive, we have intake. And then each command itself has to basically say right here, robot component.intake. So this is just saying, hey, I'm an intake command. And these robot components, you basically add one for each subsystem. So we just have the shooter, intake, and drive, and then util. This is just for like timers and stuff like that. So basically at the beginning of the season, when we're making autos, we just open this up and then add in however many subsystems we have. Now, if you notice, there's no climber here. That's because you don't climb in auto. So there's no need to add it here. And then, yeah, we saw the auto mode. It's just an array of commands. You can use auto on wait to add a delay and use like a timer. And then you can use override to kick commands out of their slot. So let's say right here, we tell the intake to be intaking down. And then here we override the intake and then tell it to be shooting. So overriding basically is just going to cancel the old command and start a new command. The reason we have to do that is because these intake commands don't actually ever, not what I wanted to do. These intake commands don't ever actually return true. They always return false. So they just turn the intake on and just keep the intake on in a loop, and they never say they're done. So the only way to cancel the command is to override it. So yeah, that's pretty much our autonomous structure. So now, obviously, you know, you can write those commands and you can make all those subsystems, but how do you actually get it tuned properly and using the sensors that you have? So what we do is first we just leave everything without sensors, just have it, you know, as we did on the single robot where, okay, yeah, I press a button, the motor turns on at a certain speed and so on. You can kind of go through your prototyping stage like that. You know, when you're just, okay, make the shooter go at 50% power and shoot a ball, see how far it goes, stuff like that. Then what I would do from there is you just check to make sure that all the encoders are actually reading the values that they're supposed to be reading. So like you said earlier with the Neo, you were checking one side was going slow. So you were checking which RPM it was going from the encoder. We would do that too. We would also check, make sure everything says it's going the right direction. So for example, if I'm pushing the driver forward, make sure it's actually, the numbers are going in a positive direction. And then just like generally what we do is if we want something to go to a certain position, we use PID. If we want something to go a certain speed, we use PID plus a feed forward, PIDF. So basically for a shooter, for example, if you use PID control, as the shooter gets closer and closer to the right speed, the motor is actually going to go slower because the P is going to become less and less, the proportional term. And that's not what you want because, you know, if you're trying to make the shooter go full speed, as it gets closer and closer, it's going to start slowing down. That's not what you want. So what you do is you instead have a feed forward term, which is basically just like kind of instead of using feedback, which is using sensors, feed forward is like using, you're just making an assumption about how something will be. So let's say you wanted the shooter to go at half speed, using feed forward, you would just tell it to go 50%. If you wanted to go at a quarter speed, you tell it to go 25%. Now that 25% might not be the exact RPM you want. You know, if your battery's low or if you have a really good battery, 25% could be more or less. So what you do is you use PID to kind of make up that difference. So instead of PID being the whole thing, you're basically doing it, you know, output based, and then PID just helps correct any of those errors. So for velocity control, like on the shooter, that's what we used. Both the Neo and the Talons have documentation on like how to best tune them and go through that process. On their like websites, they have guides. And if you're not sure what PID is, you know, there's videos explaining it, but it's basically the P means as you get close to something, you slow down. The I means over time, you should slowly speed up if you're not there. And then D means it basically just handles acceleration, so you don't change like too quickly. That's like the basic way to explain it. Another general tip is if you're doing an elevator, which is something to just go straight up and down, instead of tuning your PID, similar to the shooter, where as you lift up to the right position, the motor is going to start slowing down. And if the motor stops when you're at the right position, it's just the elevator is going to fall back down again. So what we do is we calculate just from testing what motor percentage holds the arm up in place. So you can lift the arm up halfway by hand, turn it on at 5% and see if it falls down or not. And then you can kind of figure out what percentage is enough to hold it in place. And then what you do is you just always set the motor to be going that percentage plus the PID. That way, when the PID is in the right spot, it's still going to have that little bit to hold it in place. Same thing if you're doing an arm, except instead of being constant against gravity, just based on physics, you use this cosine of the angle. So when an arm is being held straight out, you want to be going like 1.0 times whatever constant you tune. And then when an arm's straight vertical, you don't have to do anything because there's no gravity being applied to it anymore. And obviously, 45 degrees, all that, that's what the cosine it'll figure out. So yeah, that's just like a general thing when you're tuning arms. And then in our code itself, let's say, for example, the shooter, if we go to IO, this is where we actually set the PID values for the shooter. So somewhere in here, there should be a configure, shooter PID. And basically, this is where you just say, okay, my P is going to be this, my I is going to be this, my D is going to be this. You can do other stuff like the feed forward or the amount of allowable error it's supposed to have. If you don't have Talons or Neos or Falcons, what you can use instead is the built-in WPI-lib PID, which we actually ended up using on our Swerve drive because it had to use a different encoder. So here in our Swerve module, we have a PID controller. This is just part of WPI-lib you can use. And basically, you just create a PID controller, and then you set its constants, so the P, I, and D, which we have as variables. And then all you do is in the calculate function, you just say, tell the motor to be going PID controller.calculate, and then you just give it where you are and where you want to be, and it'll figure out what the PID should be. Now because this didn't exist until more recently, so we actually made our own PID, SimPID. It basically does the exact same thing where you give it a PI and D constant to have, and then you just calculate, okay, here's how far away I am from my target, and it'll kind of figure out, okay, this is how much we're going to multiply how far away we are times our P. We're going to every loop increase our I. Our D is going to be our error minus our previous error, which is basically our distance, and then divided by time. So it's like our velocity. And then basically you just do P plus I plus D, and then set the motors to be going that speed. But if you just use the built-in WPI lib, you don't have to worry about this. And same with us, like when we use SimPID, like we never change this. This is just PID is PID. So we just use it every year, just copy it over. So yeah, like in our drive, for example, in our auto modes, we were going to a certain X and Y position on the field. And that is where we would use the PID. So we have this function called drive to point, takes in an X and a Y and an angle. And basically we just say, we just figure out, okay, this is where we want to go. This is where we are. That's going to be our error. Since it's a swerve drive, we do like a vector because it's an X and a Y. But on a normal drive base, you would just have just a drive straight error. It would just be one, like one variable. And basically, we just say, hey, YPID, calculate how fast we should be going. This is what our error is. And then eventually we do some kind of limiting stuff. And then we just say, make the robot go this fast. And then to check if the PID is done, we just check, okay, are we within a certain position? is our error small? Okay, yeah, that's a good question. So how do we know in our auto, for example, our 5-ball auto, how do we know where to drive to pick up the first ball, for example, how many meters it was and all that? So what we do is every year we look at our gearbox and basically figure out, okay, our encoder has this many counts in one rotation. And then we know the gear ratio from where the encoder is to where the wheel is. And then we convert from encoder rotations to like an actual unit, like either meters or feet or inches. And then that way, when we're tuning the auto, we can just say, okay, go, this many feet. We don't have to say go, 10,000 encoder ticks, because that doesn't really mean anything when you're just thinking about it. What we like to do is push the robot on the field to and what we do is just have the robot disabled and push it on the field and just kind of write down, okay, this is where, the first ball is, it's at, 0 and then 1 on the X. The problem with the swerve drive though, is that you can't really push it. So what we did is we just had it enabled in teleop going really slow and keeping track of where its position was. You can use the CAD as well to kind of give a starting point. But you're definitely going to need to tune it slightly. You can't just go off the CAD and just type in all the coordinates and then try it. It's probably going to go too far or not go far enough. And then from there, you just kind of tune it a little bit extra. Yeah, and then over the course of the event, you might notice that your wheels have some wear on them and the autos don't go as far. You can either go in and actually manually change these points, or the way we structured it is we actually have a constant in our code, which is like the diameter of the wheel. And then what you could do is just like, as the competition goes down and your tread gets worn down, you can just change this from a 4 to like a 3.98 or something. And what we do is we actually put out a measuring tape, measure 10 feet. We then push the robot 10 feet and then check, did the robot think it actually went 10 feet or not? And based on how wrong it was, we just adjust this diameter to kind of compensate for that. Yeah, and that's something we do at the beginning of the season, basically, is figure out all the different conversions to go from encoders to actual units like degrees or feet or meters or RPM, just to make everything a lot easier to kind of tune. For vision control, so in the past, we used a thing called Grip, which basically is a graphical tool. Completely free. You can just get it from the WPI lib website. Basically what you do is you just add in a picture. Hold on one sec. Just make sure I find the right picture. And you can basically tune the vision stuff like on the fly in this program. And then based on what you find is tracking well, you can then export that into code that you can then put on your robot. Not seeing where I put those pictures. I'll just do a random picture of a robot as an example. All right, so here we are back in Grip. So what you can do is like from your driver station, if you have the webcam showing there, you can take a screenshot of that and then paste that screenshot in here. And now, obviously, you would want like the target, the vision target on the field, but we're just going to use this little green light as a target for now. And basically what you can do is start doing the vision processing. So the first thing you need to do in any vision processing is do a color threshold. Now you don't want to do RGB colors. You actually want to do what's called HSL or HSV. which is basically hue, saturation, and then luminance. And basically, what this does is basically it turns the image into what's called a binary image, where either the pixel is black or white. White is if it's past this threshold. So right now our values are completely open, so everything's passing. That's why it's completely white right now. If we turn our hue, we can kind of see some colors are disappearing. And what we want to do is just have it so only green stuff shows up, because that's the color of our the LED that we're shining at the reflective tape. So we can see there, this green is going through, and then the other stuff isn't going through. And then what you can do is just usually just turn up the saturation high, because only really bright lights are going to be very saturated. And then same with luminance, just turn that up. And now you can see we have an image that went from a total, normal image to just the green section showing up. And then what you want to do is you want to get rid of these random dots that aren't relevant. You just want to find out where this is. So what you do here is first you want to find contours, which will just find all the little pieces in the image. So right now we actually found 38 separate dots. Then what we want to do is filter these. So we only want the ones that are within this criteria to pass our filter. So what we could do is make it so that only they need to be a certain area. That's a big one. So we see all those tiny little dots have disappeared now. We can do like maximum width. Solidity is a good one. So only things that are full will pass. So like tiny little dots that have like gaps in them won't pass. Ratio is another good one. So basically, if the vision target in the game is like a rectangle that's like 2x1 length to width, you can set that ratio here, and only things that are that ratio will go through, and things that aren't that ratio won't go through. So for example, I'm saying the min and max is 1, so it needs to be like a square. Obviously this isn't a square shape, so it doesn't go through. But now that I make it between 1 and 2, because it's more of a rectangle, now this passes. But yeah, and this is basically how you do a vision pipeline. HSL, then you do contours, then you filter out the contours, and then basically this is what you would check based on what pixel this is at. That's how many degrees you need to turn. You just convert that from the resolution of the camera and the field of view of the camera. And then for grip, you can generate code, and you can just say I want Java code, and then it'll just like extract this to a file, which then has all the OpenCV code that's like doing all this. And then you just need something in your robot that's going to use this that's going to use the code that it generates. So back in 2017, that's what we used. So if we go to our 2017 code, we have sim processing. And this is the code that's automatically generated by grip. And it basically handles the blurring, all the different thresholds. It just makes the code for you based on what you did in here. So that's really nice. And then you just need to do the, you just call the one function to get back the contour positions. And then you just call process, and then it'll do all of it for you. And then we just had this camera thing, which just basically creates the camera feed. And then if we want to do vision aiming, it would basically figure out where we are, look at the different contours, find the right ones, and then return an X and Y position of where that blob is. Now, a simpler thing you can do is there's a thing you can buy called a Limelight, which probably notice a lot of teams using. Pretty much every top team in the world uses one of these to do vision tracking. No one really writes their own vision code anymore. And basically what this is it's just a camera you buy. Inside of it is like a Raspberry Pi, and it basically just does the same filtering and stuff. But instead of it running on the RoboRio, it runs on the separate Limelight. That way it can run at 90 FPS. Because when you're doing the processing on the RoboRio is not that fast. It can only do about 20 frames per second, which isn't really fast enough to use it in real time. But the Limelight, since it is kind of on its own, it can update faster. And you can basically just use it as if it was a sensor and just say, okay, how many degrees to the left is my target? And then turn that many degrees. And you can just have your PID use this as a sensor. And it kind of has the same thing where they can, you have to do the same thing where you configure the HSL values and the blobs. So what we just went through there still applies, even if you're doing it on the Limelight. And yeah, now the only problem with Limelight is that it's kind of expensive. And sometimes, like I know because of supply shortages, it wasn't really in stock that much. But like in terms of dollars per like how much it can improve your team, getting a Limelight is like definitely something I would look into. And looking at our actual Limelight code, instead of having all that complicated camera stuff that we did back in 2017, I don't even know where we do the Limelight. I know in IO we definitely create one. Yeah. So here's our Limelight, and basically all it does is it just reads these values, and it just says, you know, our target X position, target Y position, and it will just tell you how many degrees to the left or right the target is. And then all you do is make a PID that says, okay, if I'm this many degrees, turn that way. So like on our drive, for example, if we go to the aiming state, Limelight goal lock, basically what we do is we just check if there's a vision target. If there is, we just take where we are, subtract how far the target is, and then we just turn to that position. And then we just check, are we, you know, within plus or minus a few degrees of the target? Then that means we're aimed. Otherwise, we're not aimed. We also had a thing where we checked how far away we are from the goal. And if we're too close, we blink the LEDs red so the driver knows to back up, because we can't actually shoot any closer than 10 feet from the goal. So that's just kind of another thing where we kind of integrate the sensors plus the LEDs to make the robot easier to drive. And then, yeah, so just in general, when we're starting the season, we kind of start working on the robot in order of importance. So first we get the drive base moving, then we work on something simple like the intake, then we go on the more complicated stuff like the shooter or the elevator, then we would start working on the climber. And then, yeah, when you're first turning the robot on, don't have any kind of PIDs or anything. Make sure you're just doing it like manual control, and then work on the PIDs after the fact once you know that all the sensors are working. Because you don't want the first time you turn on your robot to be when, you know, the elevator suddenly decides to lift up at full speed because of the sensors weren't programmed right. So you kind of want to just take it in steps and just kind of add more things as you go along. And just like a best practice, like, you know, if, for example, our intake, we just set it to go a certain speed when you press the button. If that works and there's nothing wrong with it, just leave it like that. You don't need to add more advanced controls to something when it doesn't need it. Then I would go to adding PID. So for our shooter this year, we had a PID to get it to the right RPM. And what I would focus on is making sure that you're getting the PIDs that you need for teleop first. So you need the shooter to go at the right speed, but you don't need the drive to be able to do a PID. In auto, like that doesn't affect how you drive in teleop. So there, you should work on that later. And then, you know, if you have a camera, you want that to work in teleop and in auto. So you should do that early on too. And then basically making your auto should be like one of the last things you do after you have the teleop working and automated. And then, yeah, when you're making your first auto, the first thing you want to do is get it driving to the right positions first. So you first set it up to drive to a certain encoder position. Then I would tune it to program to turn to a certain angle using PID. And then from there, you can combine driving straight, turn, drive straight, turn. And that's, you know, for like 80 to 90% of autos, just driving and turning is pretty much all you need. You can look into other more advanced things like, you know, following certain paths, but for most teams, like you can make a good auto without doing that. And then once you have it driving to the right places, then you can start adding in the other parts, like intaking the ball, shooting the ball, stuff like that. And then, yeah, just some general advice, always have like an auto, or be ready to have your auto do nothing. You might be with alliance partners that have really complicated autos and you don't want to accidentally bump into them. At our first competition this year, I think for our first 7 qualification matches, we just didn't do anything in auto because our autos weren't ready at the time. Then we started with the easiest auto that the third robot and alliance will be doing. So for us, that was just shoot the ball that we start with and then back up out of the zone to get the 2 points. And then from there, for our second competition, that's when we added the 5-ball autonomous mode, stuff like that. It's better to have an auto that's consistent than an auto that like is, you know, really pushing the edge and driving really fast. Like it's better to shoot, you know, 3 balls 100% of the time than to shoot, you know, try and shoot 5, but you know, it only works like, you know, 1 time out of 10 or something. And yeah, like I wouldn't worry too much about doing path following. Most, like a lot of World Championship robots, especially, you know, anything from before 2017 or 18 or so, was just using PID to drive to a certain place and then turn. That's what I would focus on. And then if you got that nailed down, then work on more advanced path following stuff later. For example, even on our swerve drive this year, we just did a PID for X and a PID for Y. We didn't do any path following at all. Just to keep it really simple, because it was our first year doing swerve. And yeah, definitely you want to go to the WPI lib page. There's a lot of good information there and tutorials and stuff. As we saw with the robot simulator, and there's just steps on, you know, how to wire the robot, how to program the robot. You can see the API docs, which kind of tell you what each function does. So stuff like that is just good to know where to go if you need help. Same with like, you know, if you're using CAN motor controllers, you can kind of go here and they'll tell you how to wire them and how to program them and stuff like that. So that's very important. Our website, do we have anything important on there? I think we have some resources. Not much on programming though. And then our GitHub. So this is where we have all of our public code from previous robots and where we'll be putting our 2022 robot when it goes public. And then also we're going to be probably putting some sort of blank template for other teams to use as well. And yeah, that's my presentation.
Well, thank you very much, Kaleb. What an interesting journey through the world of 11.14's code, and lots of amazing developments in your code and techniques that you've used. And I'm sure this will serve as a really valuable resource for many teams. So just to sort of finish off our evening, I'd just like to make a little request. I'm just going to share my screen here. And invite everyone to help us with this little retrospective. We're just having the teams or the individuals in our sessions here complete a little survey, which is a little feedback on our sessions, what worked well, what might have been improved, and suggested topics for future sessions. And so that's the the process that we've been going through, and we've already received some really great feedback from this morning's session, this afternoon session, and that will help us to do some additional mentor sessions in upcoming weeks. So with all of that, I really hope everyone has had a great time. I know I have. Thank you again to Kaleb. And kindly let us know if there are additional mentor topics that you would like to discuss. I can already foresee 2 or 3 more mentor sessions developing out of the feedback that we've received from today's work. And all the best, everyone. We have 2 more sessions this week. One tomorrow afternoon, we'll have the second part of our computer programming, running from 1 to 4 o'clock, again with Kaleb. And then tomorrow evening from 6 till 9 o'clock, we'll have Ian McTavish from Team 4152 offering some more advanced CAD. And so with all of that, I think that brings us to the conclusion of this evening's proceedings, and most appreciated of everyone's participation, and particularly thanks again to Kaleb for a really wonderful session. And the CAD sessions will be available. We're trying to get up the ones from this morning as soon as possible, and hopefully we'll be able to do that soon enough. And you can keep on looking at First Robotics Canada's website for that, not website, rather a YouTube channel. Thank you. Yeah, so just in YouTube, type in First Robotics Canada, and you should be able to find our most recent files uploaded. And we'll see if we can send out some links soon. But First Robotics Canada YouTube channel. So with that, until soon, everyone, and really looking forward to our next sessions together.